Welcome to the Business Calculus lecture on optimization. Optimization is really a key word or a code word for application problems. That's word problems or real life problems that involve maximums and minimums. Let me tell you what our plan is generally. As our plan is to take the word problem and from the word problem generate a function that is continuous and see if we can't get that function that is continuous being continuous over a particular closed interval. That is, the parameters of the problem tell us to only consider certain values of x. Now, if that's the case, then what we'll do is find the absolute maximum, if appropriate, or the absolute minimum, if appropriate, by using the techniques that we used when we were determining absolute maximums and minimums over a closed interval of a continuous function. The extreme value theorem guarantees that those will exist, and it tells us to look at the endpoints and at the critical numbers. So that's our plan generally. Now, not always will we be able to stick with that plan, because sometimes we do not have a closed interval, or sometimes we do not have a continuous function. But overall, that's what we're going to try to accomplish. So here we go. Let's look at this very first problem. A garden is to be laid out in a rectangular form and protected by a chicken wire fence. What is the largest possible area of the garden if only 100 feet of chicken wire is available? Well, now I'm going to give you some guidelines that will not be applicable for every problem, but many times it will be, and so that's kind of where we'll start here. Step one, if it is a geometric type problem, we'll draw a representative diagram. So we'll draw a diagram and label the appropriate parts. So in this case, we're talking about a rectangular garden. And so that's where I'm starting here. I'm just going to draw a rectangle. And I don't know the dimensions of this rectangle. And so that's the reason I need to label. So I'll call maybe this width, I'll call that an x value, and call this length a y value. Okay, just as I've seen it here. Now, step two, and this is a critical step. Step two is to identify or create, sometimes we might say create, identify the primary equation. Now, here's where we are with this. We're looking for an area, and that's really what the key word is largest possible area. And so as soon as we hear largest, we're thinking maximum. And as soon as we hear area, oh, that's what we're trying to maximize. So we're always looking for these keys. What is it we're trying to maximize, or what is it we're trying to minimize? And in the case here, we're trying to maximize an area. So the primary equation is an area equation in this case. And so I'm going to call area, I'm going to identify that as an A. And how do we calculate the area of this garden? Well, it's the width x times the length y. That's just what? Or length times width. Okay, that's how we calculate the area of a rectangle, isn't it? So that's our second step. Now, our third step is going to not always take place like this, but here's our problem. We need to maximize A, and it consists of the variable x and y, two different variables. We need to get A to be about just x's or A to be just about y's, because we're going to need to take the derivative of this to find the critical numbers. That's really the issue here. So as we look at the original problem, there's some more information. And so what we're going to do is to identify any other equations. And in this case, I'm going to call them secondary equations or a secondary equation. Oops, secondary. Now here's what we know is that the garden, we only have 100 feet of chicken wire available. So that means the perimeter can't be more than 100 feet, can it? And the perimeter we would calculate is we've got two sides of x and two sides of y. And so we have 2x plus 2y is going to be 100. Okay, that's our secondary equation. Now, the usefulness of the secondary equation is not only do we need to identify it, but then we need to use it to eliminate a variable in the primary equation. In other words, what we need to do is we need to replace the x in the primary equation with stuff about y, or we need to replace the y in the primary equation with stuff about x. And so what I'm going to do is I'm going to solve 2x plus 2y equal 100 for y. And then I'll put that new y value in this spot. And when I solve it for y, it will have things about x in it, won't it? So to solve this for y, I need to subtract 2x from both sides. Okay? And then I could say divide by 2, but that's going to create a fraction. So what I would rather do is multiply both sides by 1/2. That will create my y, and of course on the other side, whoops, I got ahead of myself there. On the other side, when I multiply by 1/2, I'll have 1/2 times 100, which is 50, and 1/2 times a negative 2x, which is just minus x. So now I have the y value to substitute back into the primary equation. So now I've got a is equal to x times, instead of y, I've got this value of 50 minus x. So x times 50 minus x. And then, of course, now I have that as a simplified form, 50x minus x squared. So I have my area or my primary equation in one variable, and now I'm in a position that I can maximize. So step 3 will be to find the critical numbers. Step 4. Find the critical numbers of the primary equation, the critical values. Well, that means I need to calculate a prime, doesn't it? So a prime is going to be 50 minus 2x. And then, of course, I set that to 0 and solve and get x is equal to 25. Now, here's an additional step. And as usual, I'm running out of room, aren't I? Identify the feasible domain. In other words, what are the restrictions on x? Can x be any value? Can x be 500? Can x be negative 2? Well, clearly, x has to be positive, but, I suppose we could have a ridiculous situation and say the width was 0. So what we do know is that x certainly has to be greater than or equal to 0, doesn't it? Now, also, we have only 100 feet of wire here. And so if we used all of that for x, and we've got 2 x's, then we couldn't have x be more than 50, could we? Because 50 and the other side 50 would take up all that 100. So we also know that x is was less than or equal to 50. Now I recognize that it's silly to talk about x being 0 and x being 50, but we want a closed interval, and certainly this function is defined for x equals 0 and x equals 50. And as long as it's defined, then that's a reasonable closed interval. So here's where we are then, is that we have 3 x values to consider. See, we have the 2 endpoints. So one of the endpoints, okay, what is this feasible domain? Well, as a closed interval, it's the interval from 0 to 50, isn't it? See, and I'm thinking back in terms of the extreme value theorem. So the endpoint 0 is something that we need to be concerned about. And the critical number 25 is an x value we need to consider. And then the endpoint x equal 50 is the last number that we need to consider. We know that we'll have a maximum using one of those values. And we'll also have a minimum as far as that goes. So we calculate the area when x is 0. And so the area would simply be, what, 50 times 0 minus 0 squared, which is 0. Well, that's kind of a degenerative situation, isn't it? That's kind of almost silly. If x is equal to 25, then a is what? 50 times 25 minus 25 squared. Well, 50 minus 25 is 1,250, and 25 squared is 625, and so we actually get 625 in this case. So 625 is the area there. And then when x is 50, then we would calculate the area to be 50 times 50 minus 50 squared. And that's actually 50 squared minus 50 squared, which is 0, isn't it? So the absolute minimum on this interval is 0 area, and the absolute maximum is 625. So let me write on the side, since I've run out of space here. We have the maximum area that can be generated is 625, and in this case it's square feet, isn't it? Square feet, because we were measuring in feet, and I didn't write that down previously. So this is the answer to the problem. Now, this wasn't asked, but we could certainly find the dimensions, couldn't we? Because we know the x value is 50, so we know x is 50, and what about y? Well, excuse me, not x is 50, x is 25. My bad. X is 25. 25 what? Feet? So two of the sides are 25 feet, and y we can calculate using the equation that we've got right here, can't we? So y is 50 minus x, or 50 minus 25, which is 25 feet also. So to get the maximum area, we need a 25 foot by 25 foot rectangle, which is basically, is a square, isn't it? Well, this is a simple type problem. We'll continue to increase the difficulty, and so we'll stop here and look at example 2 in just a moment. Example 2 of our optimization problems, and remember, optimization just means applied problems that involve maximums and minimums. We're going to use the same idea that we used on the previous problem. In fact, this is similar, but a little more complicated. As you can read, a rancher has 3,000 yards of fencing to enclose 2 adjacent rectangular pastures of equal size along a straight riverbank. If no fencing is required along the river, what is the maximum total area that can be enclosed? So as we did before, let's look at a diagram. Let's create some kind of picture. Okay, so I'm thinking that here we've got a river, and we're assuming this straight riverbank, and so here the water's flowing through here, and so on and so forth. Okay. Now the rancher is going to build 2 pastures that are adjacent to each other. That is, they're connected. They're going to actually share a fence line. So that's the big area. Let's see if I can get about halfway there. So there we go. I'm assuming now that there's equal size, and so the dimensions along this direction are the same in both cases. So, and the dimension here, of course, all the way across. I'm going to call this dimension x. So there's a section of fence that is X yards long, and there's that same section. That section would also be X yards long, wouldn't it? And likewise, this one would be X yards long. I'm going to call this amount Y, and so this amount is also Y, because these are equal sizes, right? And of course, along the river, which is here, we're not using any fence at all. So there's kind of a diagram that illustrates what's going on. Now, remember, we need to next decide what the primary equation is. And that's really what we need to focus on. And it's really easy to get distracted and try to do something else using all the information that we see in our diagram. But we need to drill in on what are we doing. We're maximizing an area again, and it's a total area. So one more time, we need an area function. An area in general is length times width, or width times length. Well, we're looking at the total area, so we're not looking at one of those pastures, we're looking at both of those pastures for the total area. So in this case, let's say that the length is Y plus Y, or 2Y, and the width is X, isn't it? And so that would give us the entire, the rectangle not split in two. But here we go again, we have one primary equation, and this is what we need to maximize, the area equation, but it involves two variables. And so there we're going to look for a secondary equation. And the secondary equation here is going to have to do with how much fence. It's similar to what we saw earlier, is how much fence do we have to work with? Well, we only have 3,000 yards to work with. So that means if we add up all of the sections of fence, that's the X along here, and the X along here, and the X along here, and this Y, we actually have what? 3X plus 2Y is going to be equal to 3,000. Now this isn't a perimeter, it's just these sections of fence that we're noticing in our diagram. Well, if we can take this equation and solve for either X or Y, then we can replace the X or Y in the previous equation and have just one variable. I kind of like X's, so I'm going to solve for Y. See, I'm going to replace Y when I say solve for Y. And so I would subtract 3X on both sides. Now, and so next I would probably multiply through by 1/2 or divide both sides by 2. I'm noticing right here that really what I need to replace, or I could replace, is a 2Y, couldn't I? And I already have the value of 2Y right here is 3,000 minus 3X. And so now the next step is to eliminate, and in this case, what am I eliminating? I've decided when I solve for Y, I'm going to eliminate Y from the primary equation. So I'm going to rewrite it as A is equal to, instead of 2Y, 3,000 minus 3X times the X value. Now, I was fortunate here, and I want to point that out. I was kind of fortunate here. You know, most of the time, I wouldn't have noticed that. So let me just show you what would have happened if we would have solved for Y. I would have multiplied both sides by 1/2. Or maybe I could just say divide by 2. I'd still get Y is equal to, and then I'd have 3,000 minus 3X all divided by 2. That other side divided by 2. And then I can say, okay, in the place of Y, and remember, A is 2Y times X. So in the replacement of Y, I'll have 2 times the fraction, 3,000 minus 3X divided by 2, and then times X, because that's the Y value. But I'm ending up multiplying that fraction with the 2 that was in front, and so I still end up with a 3,000 minus 3X times an X, don't I? So I get the same result. It was just a little quicker when I made that observation. And so Now I have A is equal to, I'll multiply that out, 3000x minus 3x squared. So I need the critical numbers. Okay, so that means I need to find A prime. And A prime will be what, 3000 minus 6x? And so we'll set that to 0 because I want to know where the derivative is 0. And when I solve this, I'll get x is equal to 500. Okay, so I have one critical number. Now, the next issue, remember, is what we would like to do is to see whether we can define a closed interval for which the function is defined on. Okay, and we call that the feasible domain. That is, what values of x are feasible here. And we certainly know that x has to be bigger or equal. It could be equal to 0, although it would be a nonsense problem. Our function is certainly valid. That is, 3000x minus 3x squared is certainly valid for an x value of 0, isn't it? So that's a reasonable value from the function point of view, is that we would just never have a dimension of 0. But we could have it a little bit bigger than 0. Now, I'm also claiming that x has to be less than or equal to 1000. And here's the reason for that, is I've got 3 of these x's to add together along with 2 of the y's. But I only have 3,000 yards of fencing. So if I have 3 x's, none of those x values could be more than 1,000, or I would have more than 3,000 yards of fencing. So the feasible domain is the interval from 0 to 1,000. Now that's a closed interval. Certainly the function is defined, although 0 and 1,000 probably would never be values that would make sense for us. Okay, so x equal 500 falls in that interval, doesn't it? It's between 0 and 1,000, and so that is a valid critical number. And so now I'm just going to be worried about evaluating the area for the critical number and the 2 endpoints. So I've got an x value. I'll have x values of 0, 500, and 1,000, and an area value that will go with each of those. So for instance, when x is 0, I'll calculate the area. When x is 500, I'll calculate the area. And when x is 1,000, I'll calculate the area. Because remember, from the extreme value theorem, we have to have an absolute maximum and an absolute minimum on this interval from 0 to 1,000. Well, remember, this is the area function right here. And so when we put 0 into that, we get an a value of 0. Now, when we put a 500 into that, it's a little different story. We'll have 3,000 times 500, minus 3 times 500 squared. Oh, that's going to be a big number. Let's see, 15, 0, 0, 0, 0, 0. So what is that? 1,500,000 minus 500 squared. Well, that's going to be 25 and 4 zeros, isn't it? So that's 250,000 there. And we end up with 1,500,000 minus 750,000, which is going to be 750,000. So for the x value of 500, the area is 750,000, in this case square yards. And then in the case of a being 1,000, x being 1,000, we just do the calculation again, so we'd have 3,000 times our x value of 1,000 minus 3 times 1,000 squared. And with a bit of calculation, in this case, we would find out that that value was 0. This is kind of like the original, the very first problem we did, but we can't assume that those endpoints are going to give us 0 each time. Don't make that assumption. So the absolute minimum area is 0, okay, but the absolute maximum area is 750,000 square yards. And so to answer the question, the answer is the maximum total area possible is 750,000, and the units, because we're talking about area, are square units, and in this case, we're talking about yards, aren't we? So square yards. Doesn't that empower you? Don't you feel very smart now? Okay, well, let me prepare for the third example. We'll stop this one and go on. Okay, as you can read, for example 3, we're going to create an open box, meaning that it has each 4 sides and a bottom, but no top. An open box is to be made by cutting a square from each corner of a 16-inch by 30-inch piece of sheet metal and then folding up the sides after we cut out those squares. What size square should be cut from each corner to produce a box of maximum volume? So diagram first. I'm just going to, let's see what we've got here. Okay, now here's my 16-inch by 30-inch piece of sheet metal. And what we're told is we're going to cut out a square from each of these corners. So it's going to look something like this when we cut out the square. Okay. Now remember, those squares are going to be gone. That part of the sheet metal is going to be gone. So when that part of the sheet metal is gone, then imagine that we have these flaps. See, I'm putting these dashed lines of where we're going to fold this up. Now, of course, we want to know about what size square to cut out. And they're squares and they're all the same size. So I'm going to let the dimensions of the square be an X, okay? And so that's the same for all of those 4 squares. Now remember that the original dimension of the sheet metal in this direction is 16 inches, and the original dimension of the sheet metal in this direction is 30 inches. Okay? Now, what we're going to do is we're going to take that sheet metal and we're going to fold up the sides now after we cut out those squares. So imagine that, then, okay, let's see if I can draw something that might resemble what we're doing here. If I would have known that I was going to have to draw teaching math, then I would have taken regular art when I was in college instead of art appreciation. That's a little poor humor, I recognize, but a little humor. Whoops, I've run into a problem up here at the top. Okay, can you imagine that box? So the dimension right here, see, this dimension is this part of the box, okay, that dimension. Now, it's pretty important here to recognize that this dimension of the box, in fact, let's pause for a moment. Remember, we're going to need a primary equation. And this is a place where we get off track again. I mean, we could easily get off track because what's asking us is what size square should be cut. But now we need to concentrate on what it is we're maximizing or minimizing. And see, we're maximizing a volume. So our primary equation has to be a volume equation. And so it's the volume of the box, and the way we calculate the volume of the box is length times width times height. And so we need each of the dimensions of the box that we have laid out here. And so when I'm looking at this dimension, remember we've got an X that we cut out here, an X that we cut out here, and all the way across was 16. So that dimension is the original 16 inches, but we're cutting out x from each end, so we're taking 2x away from that side. So this dimension right here is 16 minus 2x. Now, in a very similar fashion, the dimension that we'll have here, which corresponds to this side, we started out with 30, but we're cutting x from each end, and so this dimension is 30 minus 2x. And so this long side ends up being 30 minus 2x. Now, when we fold these sides up, then it's this dimension that's going to be vertical, isn't it? And so this vertical dimension, this height, if you will, is the x amount, the part that we cut out. Okay, you can imagine that. So we can create our primary equation now. V is equal to, well, the length is 30 minus 2x. And the width is 16 minus 2x, and the height is just x. Now this is a little different problem than what we've had previously, because in the past we needed a secondary equation to eliminate a variable, but we have only x's in this equation, so we don't need to worry about a secondary equation, do we? What we do need to do, though, is to go ahead and expand this, that is, multiply everything out. So as I multiply those binomials out, I'll have a 30 times 16, which is 480, and I'll have a 30 times a negative 2x and a negative 2x times a 16, and so that ends up being what, negative 60x minus 32x, so it's negative 92x, isn't it? Negative 92x. And then negative 2x times negative 2x is a plus 4x squared, and we still have to multiply that with x. And so what I'm going to do is kind of do two things at once. I'm going to multiply x and 4x squared and get a 4x cubed, and an x with a 92x and get a 92x squared, and an x with a 480 and get plus 480. So I've kind of rearranged it simultaneously. Okay, so this is the function that we need to maximize. And to maximize, then what we need to do is to find any critical numbers and a closed interval that makes sense for these x values, and then just check at the endpoints and the critical numbers. Okay, so critical numbers next. So we need to find v prime, don't we? Well, let's do that right down here. V prime is equal to, what, 12x squared minus, what is that, 184x plus 480. And so we need to set that equal to 0 and solve. Now, I want to do this the easiest way I can, and I might guess that 4 is a common factor, or 6 or something else, but I can clearly see 2 is a common factor, so I'll factor it out. And so that'll be 2 times 6x squared, what, minus 92x plus 240, is that right? Yeah, that's right. And I see now each of those is still has a factor of 2 in them, so I'll factor out another 2, and so this will be 3x squared minus 46x plus 120 equals 0. Because I actually have a 4 factor in front of that, don't I? I'll divide both sides by 4 because this doesn't include a variable, does it? So that's 4. I'll just divide both sides by 4, and I'll end up with 3x cubed. Oops, I put cubed, but it's squared, isn't it? 3x squared minus 46x plus 120 is equal to 0. 0 divided by 4 is still 0. And then I look to factor that. If I couldn't factor it, then I'd have to use the quadratic formula. But I'm going to attempt to factor this, and clearly I have to have a 3x times an x, and all my signs have to be negative. And I think, let me look at this. Let's see, how about 10 times 12? Will that work? Let's try the 10 here and the 12 here. Certainly that gives positive 120, and I get a negative 36x by multiplying the outsides and a negative 10x by multiplying the insides. Negative 36 and negative 10 is negative 46. So that is factored, isn't it? Okay, well, I set each of those to 0. And we'll kind of streamline this. So we'll get x is equal to, from the factor right here, when I set it to 0, I'll get x is equal to 10/3, which happens to be what, 3 1/3? And when I set this factor to 0, I'll get x is equal to 12. So I have two critical numbers. Now, I need to, before I go further, I want to make sure that those critical numbers are feasible. That is, what's my feasible domain here? Well, here's what I notice. That this dimension, see, this dimension right here, 16 minus 2x, that dimension is 16 before I cut anything out. And certainly I couldn't cut out more than 8, because then I would, I'm cutting out 8 on each side, or more than 8 on each side, and that would be more than 16 I'm cutting out. So I know my x's have to be less than 8, less than or equal to 8. And of course I wouldn't have a box if I didn't cut out, if I cut out 0. I certainly can't cut out a negative amount. So I'm claiming the x values have to be between 0 and 8. And of course, obviously, those would be degenerative situations, but the function at least is defined. That is, the volume function up here is defined for those x values. And so the closed interval I'm considering is the interval from 0 to 8. Now, that becomes particularly significant here because this critical number is not in this closed interval, is it? 12 is not between 0 and 8, and so I don't need to consider that critical number. Okay, well then here's where I go. Now, we're kind of assuming this, but we want to make sure that we get a maximum value when x is what, 10/3? So we only have, and we're talking about volume here, aren't we? So we only have 3 values to try. The endpoint 0, the critical number 10/3, and the endpoint 8. And we calculate the volume for each of those. So when we put where am I? Oops. Way back up here, I see I made a mistake. This was actually a 480x. Now, I took the derivative correctly, but I failed to put my x there, didn't I? I bet you caught that. So when x is 0, then I put a 0 in for x, and I get a volume of 0. When x is equal to 10/3, and this is a mess, my volume I would calculate by putting a 10/3 in for each of these x's. So that'd be 10/3 cubed, 4 times 10/3 cubed, minus 92 times 10/3 squared, plus 480 times 10/3. Now we could go through that arithmetic, but I'm going to tell you what I got. I got 19,600 divided by 27. Now, when I write that as a decimal, of course, it goes on, I think, a little further than this, but I get approximately 725.9, what did I get, 926 maybe? But I might as well, that's close enough to 726, isn't it? Okay, so my volume in this case is about 726, a little bit less. And then when I calculate x to be 8, or when x is 8 and I calculate the volume, in this case, as strange as it seems, and I warned you not to always depend on this, but we end up getting a volume of 0 again, I believe. Yes, we will. Okay, so here is our maximum. This is an absolute maximum volume on the interval from x equals 0 to x equals 8. Those are the only x values that have any chance of making sense. And so that happens when x is 10/3. So the original question was, what? What size square should be cut from each corner? So the square should be a 10/3 inches by a 10/3 inches to give the maximum volume. And that's, what is that, 3 1/3 inch by 3 1/3 inch. That's the size square that needs to be cut out, maybe we could say it that way, to give us the maximum volume of 726 cubic inches. But we were asked for the size of the square. Well, that ends example 3. We'll look at example 4 here next.